And we're going to use the same historical convention that counterclockwise rotations is positive. So here's a fan blade, and we're told that it's speeding up. You just turn on the fan, so the absolute value of omega is getting larger. But what are the actual signs of omega and alpha? Responses. So you can see from the diagram that it's rotating clockwise. That means omega is negative. So it's got to be C or D. Then you're also told the fact that it's speeding up, that means that alpha has the same sign as omega. What about if it's slowing down, and there, it's a little hard to see this diagram, but the diagram looks like that, sorry. So for me, I see now that it's going counterclockwise. That means omega, which is what it's moving as, is going to be positive. And then it says that it's slowing down. That means that alpha has the opposite sign of omega. So since omega was positive, alpha should be negative. Which dumbbell has the larger rotational inertia about the midpoint of the rod? So we're going to set up the rotational axis to kind of in the middle here. Masses are different, right? Dumbbell B has m over 2 as these masses, and dumbbell A has m as these masses, but there's also a distance. So I think this distance right here is actually r over 2, whereas this distance right here is r. But basically this one is going to be, IA will be m times r over 2 squared plus m times r over 2 squared. Okay, so that's equal to 2 m r squared over 4. So I think IA is equal to mr squared divided by 2, because 2 over 4 is 1 over 2. And IB is going to be m over 2 times r squared plus m over 2 times r squared. So, which is just mr squared. So what matters more than the mass actually is the distance from the mass. When we change the distance of these masses, if you double it, you increase the rotational inertia by a factor of 4. So I would say here IB is greater than I. Mass, M2, sits on a frictionless table. We sort of did this before, but the difference here is that now the pulley has its own moment of inertia and its own mass. I guess it's still frictionless though. It's attached to a cord that wraps around a massive pulley of radius r and is attached to a hanging mass M1. Assume the axle of the pulley can rotate without friction. After the system is released, how does the magnitude of the tension in the rope, T1, at the bottom there, compare to the weight, M1 times G? So with this pulley here, is that it's a M1 up on the top is on a frictionless surface. And there's a tension, clearly, in the string. So will M1 accelerate? Yes, it has to, right? Because it's going to get pulled to the right. So the question is, since it's attached, so I guess the pulley's also going to accelerate. It's attached to M2. Will M2 accelerate? Yes, it'll be accelerating down. And then you think of the free body diagram of M2. You've got tension and T1 pulling up. You've got M1G pulling down. It's accelerating down, so M1G has to be greater than the tension pulling up, or else it wouldn't accelerate down. Now it's asking how the tensions in the two ropes compare. I like A, that the T1 is greater than T2. The idea is, and I don't know what I was saying before, M2 is sitting on the top, and that's on a frictionless surface. It's being pulled to the right. M1 is the hanging mass. It's going down. Okay, so those two things are still true, even with a massive pulley. But now, since M1 is going down and M2 is going to the right, if the string is sticking to the pulley, it means that the pulley, I think, has to have angular acceleration in the clockwise direction. Okay, so as this thing is speeding up as it falls down, it's going to speed up the pulley's acceleration. So what does that mean? It needs to have a torque that is clockwise. And where does the torque come from? It can't come from gravity or the axle or something. It has to come from the difference in the torques of the two tensions. And the tensions Tension in the top rope, T2, is actually pulling it in the wrong direction, and T1, pulling it down, is pulling it in the right direction. So T1 has to be greater than T2. If you release this pulley, you release the whole system, what's the torque in the pulley? A lot of people are saying B. That was the one that I got as well. So the way I worked that out is, I like to draw this a little bit bigger. And here's your rotation axis. Here is R. Those are perpendicular. There's T2 pulling on the pulley. And then here is T1. And here again is R. And so what you get is T2 times R and T1 times R. Those are the magnitudes, but then you figure out whether they're plus or minus based on counterclockwise or clockwise. So I think T2, it makes it want to go counterclockwise, so that's a plus. And then for T1, it makes it want to go clockwise, so that's a minus. Which description below best describes the moment of inertia, often given the symbol I, and measured in units of kilogram meters squared? The rotational analog of kinetic energy, B, the rotational analog of mass, C, the rotational analog of momentum, D, the pivot point in a static equilibrium problem, or E, the tendency for anything that is rotating to continue rotating. So the one that I wanted was actually B. I think it's better than any of the other ones there. So basic idea is that when we had that whole analogy chart, I had Newton's second law, which was that F equals the mass times the acceleration. And then for rotation, you have that the torque, and this is net, the net force is the mass times the acceleration. If things are moving in a line, the net torque, if you're trying to spin something, is equal to I times alpha. So alpha is a vector which can be counterclockwise or clockwise. Same with torque. We're going to actually talk about the vector nature of torque and alpha and omega. You can define a new vector which is perpendicular to the plane of rotation using a new right-hand rule. So this is the I here is the analogy of mass. It's the thing that kind of prevents something from accelerating too much when you've got a net torque. Another good way of doing these is that you sort of flip it if you want cause and effect. The net force causes something to accelerate, and the mass is what prevents it from accelerating. The higher the mass for the same net force, you have less acceleration. And the same thing here for angular acceleration. The net torque gets it accelerating, but the rotational inertia is what keeps it from accelerating. And remember, acceleration can be slowing down or speeding up, right? So if it's got a very large moment of inertia and it's already spinning, it wants to keep spinning. So it is related to the tendency for anything that is rotating to continue rotating, I guess. So E is not a bad answer. If A was 2 meters east and B is 3 meters north, what's A cross B? Let's go at the graphics there. Does that make sense? So you knew it was going to be up or down because the two vectors that you're cross-producting are in the horizontal plane. But the question is it up or is it down? And that's when you use your right-hand rule. V is 1 meter per second down. B, which is the magnetic field actually, is 3 Tesla south. So I don't know if you know about Tesla. Tesla is a unit. It's the SI unit of magnetic field. And magnetic field is a vector. So it's down. So what's V cross B? A lot of people were saying that's west. I like that. So again, north is that way. South is that way. V was down. And then you bend it south. So now my thumb is pointing west. So yeah, last one. V is 4 meters per second south. B is 2 Tesla, also south. What is V cross B? You got it. You can't cross product things that are in the same, they're parallel. And don't forget the magnitude has a sine theta in it, where theta is the angle between the two vectors. Parallel vectors, if you're going the same direction as the magnetic field, you're not going to get any force on you. So a person spins a ball on a string in a horizontal circle, and then another person with the racket hits it. So what I'm going to do is, as it's going by, give it a sharp blow in the forward direction. This causes a change in angular momentum. So you can either think of this in terms of the torque of the hit, the force crossed with the r vector, or in terms of what's the direction of the momentum, angular momentum, does it increase it or decrease it? Ready? Okay, good. I missed it. Oh, okay. Gotta try not to hit my son. Whoop. Whoa. Are you okay? All right, thank you very much. Ooh, it's a split between the plus x direction. So the force is in the plus x direction, but that's not the direction of the angular momentum. Angular momentum's in the plus z direction, okay? So there's momentum. So actually what I'm doing is I'm giving linear momentum in the plus x direction. So P, delta P, is in the plus x direction. This is what's called linear momentum. But there is another thing called angular momentum. This is L. So delta L, it gets bigger, right? Goes up. Because I've sped up the ball by whacking it in the same direction it was already going. So now the delta L is in the same direction as L. And actually, it makes sense with the torque as well, because now you've got R being the distance from the center of the circular motion, which was Mirage, out to the ball, and then F, which is the force going out from my tennis racket. So you've got R cross F, and now your torque is in the plus Z direction as well. And that torque is equal to the change in angular momentum. A figure skater stands on one spot in the ice and spins around with her arms extended. When she pulls in her arms, she reduces that moment of inertia or rotational inertia, and so I goes down, omega goes up. So compare her initial rotational kinetic energy to her final rotational kinetic energy. So A is correct. So let's call this 1 and call this 2. So certainly I1 is greater than I2. So E1 is equal to 1/2 I1 times omega 1 squared. And also I know that I1 times omega 1 is equal to I2 times omega 2. So omega 2 is equal to I1 over I2 times omega 1. So then the energy 2 is equal to 1/2 I2 omega 2 squared. So let's sub this in. Let's take this and plug it into here. I get 1/2 I2 times I1 over I2 omega 1 squared. There's a lot of things going on here, but there's an I2, there's an I1 squared over I2 squared. This cancels this. You get omega 1 squared. You can write this as 1/2 I1 omega 1 squared times I1 over I2. See where I'm going with this? So that I say that E2, her final energy, is E1 times this ratio I1 over I2, which is greater than 1. Where does the energy come from?
The person pulling the arm in is doing internal work.
Yeah, so that's exactly correct. The person pulling her arms in is doing work on herself somehow. A car is driving east on Bloor Street. What is the direction of the angular momentum? So they've got north, east, southwest, or up and down. This was on the pre-class survey, that if you're driving this way, this is east, then the wheels have to kind of rotate this way. If you're driving towards the right, the wheels are rotating clockwise. So then you bend the fingers in your right hand in the direction the wheels are turning, and your thumb points in the direction angular momentum vector is, or the omega vector, actually. We'll talk a little more about this, especially when we get into the gyroscopes. It's super important. It's a bit hard to draw this, so what I'm going to do is I'm going to draw it like this. Okay, so if I draw a circle with an X on it, this means into the page. And if I draw a circle with a dot in it, this is out of the page. It's a notation which is pretty handy when you're doing 3D stuff. And I kind of think of it as maybe if the arrow was like a cone or something and it was pointing right at you, you'd see the little pointy end as being that dot. But if the arrow was going away from you and it had maybe feathers and an X pattern or something, you were looking at the feathers. So this, into the pages, you're seeing the feathers of the arrows going away from you. And the dot is that the pointy end's coming at you. So, and then, you have to think think that's north. If east is to the right, and north is into the page. So let's say we release something from rest, a solid disk, for example. I have one of these, and I let it roll without slipping down an incline. And at the same time, I release a frictionless block of ice, which can slide with somehow zero friction. Sort of a thought experiment. We didn't bring the frictionless block of ice today. I guess if it was frictionless, the solid disk would just slide along with no friction. So why does it roll? Well, it's spinning because of the friction. And that friction is one of the forces in the net force on this. So it's got to slow it down a little. If you think about the energy, I think some of the energy is getting used up in the spinning of it. At the beginning, all of the energy is in U, or potential energy. PE, gravitational. It's all in that. And then as it goes down the hill, the potential energy of gravity, the mgh, goes down, and then it gets provided to, in the case of the block of ice, 1/2 mv squared. It all goes to 1/2 mv squared. But you've got the same amount of energy if you drop the same height going into the spinning object, and it has to get split between, part of it will go into 1/2 mv squared, and then part of it will go into spinning it. And so if you have to split the energy, they're both a little less. So it has to go slower. What if we do the hoop versus the solid disk? Now, John says that these are both about the same mass. A wooden disk versus a metal hoop. This one's a lot more dense, but all the mass is around the edge. And this one is more of a solid. So I'm going to release these from rest and see who wins it. Survey says solid disk. Interesting. 1, 2, 3, go! Okay, you guys got it. Since the rotational inertia of the hoop is greater, it sucks up more of the rotational kinetic energy, thereby reducing the translational kinetic energy, the 1/2 mv squared. So that's going to reduce the V, I think. What we're going to do is race these two cans of soup. One is chicken broth, condensed chicken broth, but it's, if you can kind of hear it, it's sort of sloshy. It's low viscosity liquid. The cream of mushroom soup, however, is really sticky. And no, before you add water to the cream of mushroom, it's almost kind of like a solid glutinous mass. So it was good to see what really happens. Whoa, look at this. Slight in favor of cream of mushrooms. Okay, chicken broth, we'll put that in front, right there. And the cream of mushroom, we'll put that up here. Okay? See? Release them from rest. See who wins. Mark, get set, go. Looks like this chicken broth has won. This is more of a fluid dynamics problem than really a physics question, so sorry about that. But let's go over why I think it's happening. This surprised me a bit when I saw this. This is what I think is happening. The cream of mushroom soup must rotate because it's all stuck to the inner surface of the can. So it's almost like a solid disk, and we'll probably be rolling down the hill with an acceleration g sine theta divided by 2, I think. Or sorry, divided by 2/3, I guess, divided by 3/2. So, but the chicken broth, I think maybe it's just not rotating. It doesn't need to because it's probably just slipping down the hill. It might slosh a little, but maybe all that water just kind of goes down without rotating. And then it's almost like a frictionless block of ice. It's just the can is rotating without the... I know the chicken broth wins every time, but it's a little hard for me to understand why, but I think this is it.
My name is Jason Harlow, and I hope you enjoyed this video. If you have time, please fill out the feedback form on my Google Forms available in the description to this video. There's also a link to the Google Classroom where there's a public discussion forum and a place where you can ask me a lot of questions. Also available as a link in the description to this video. I look forward to hearing from you. Take care.